Howdy, it's Mr. Russell coming at you today with gas stoichiometry. The untrained eye will see gases as weightless, and because you don't really feel any kind of weight from a gas, and you almost don't even notice that it's there most of the time. But remember, those gases are just particles, and those particles do take up some amount of space. Since they take up an amount of space, they will have some mass. Even though there's a great distance of empty space in between those molecules, they still will have some mass. That's known as the molar volume. And they will, a gas at ideal conditions will occupy a space of 22.4 liters. More exact is 22.42. And that's 1 mole of gas. Any gas will occupy that amount of space. It's about that big. I got a box of it in my classroom. And remember that at ideal conditions are low pressures and high temperatures. So think of summer. Students behave ideally during summer. So low pressures and high temperatures. In this problem, calcium hydride reacts with water to produce hydrogen gas via this reaction pictured shown. So ask yourself this question: is it an acid-base, a precipitation, or a redox reaction? Well, it's a redox reaction, and you can see that it's a balanced redox reaction as well. Assuming a complete reaction with water, meaning assuming 100% yield, how many grams of calcium hydride are required to fill a balloon, total pressure of 1.12 atmospheres at 15 degrees Celsius if its volume is 5.5 liters? Okay, so start writing down known information. I write down my pressure, my volume, and my temperature, and convert those to Kelvin. And I am able to see that it's going to be the ideal gas law. I know that my number of moles is unknown, and I'm looking for the grams. So I'm looking for grams, so let's look for moles first, then convert to grams. And I'll use the ideal gas equation and plug in my numbers to find my number of moles. Now that I've done that, I'm looking for, I need to convert the moles of my hydrogen gas to moles of calcium hydride. So you wouldn't be able to go directly from the ideal gas equation and directly solve for the calcium hydride, because calcium hydride is a solid. So in the ideal gas equation doesn't apply to any solids or liquids. It only applies to gases, and the only gas that's here is the hydrogen gas. So that's why the answer that I get is in moles of hydrogen gas. Then I convert moles of hydrogen to moles of calcium hydride, and then just convert moles to grams, using the periodic table to get our final answer of 5.49 grams. You can also see an equation like this, or reaction, an example like this. How many liters of nitrogen are required to produce 115 grams of ammonia at STP? So it didn't give you an equation, so could you write the equation yourself? With a little help, I'll help you along and show you that the equation is nitrogen plus hydrogen to yield ammonia gas. And so I'm going to start off with my 115 grams of ammonia. I didn't need the ideal gas law for this question, because it didn't give me any of the pressures or anything like that. I can just use, since these are all gases, I can just use this equation. Start off with 115 grams of ammonia, convert grams to moles, and the moles to, you apply the mole ratio from the equation that I just came up with, and or that you just came up with. And then this last step, I am applying the molar volume. The molar volume is always going to be 22.4 liters per 1 mole. It doesn't matter what what gas this is. It could be nitrogen, carbon dioxide, helium, any type of gas. It will still always be 22.4. You don't have to go to the periodic table. Just remember 22.4. And then my final answer is going to be 75.7. We can actually see it and get an understanding for the molecular weight and the density of a gas. Those two will be related to each other by looking at exactly what the moles are. The moles is the mass divided by the molecular weight, or the value that you get from the periodic table, the molar mass. So the mass divided by the molar mass will give you your moles. So now I'm going to substitute this value of N into the ideal gas equation. So that's what this one's doing. This is the ideal gas equation, but with mass over molecular weight substituted for N. Since the mass divided by volume equals the density, grams over liters, then the pressure is the density times R times T divided by the molecular weight. That's the molecular weight from the periodic table. We can rearrange these again to find the molecular weight equals the density times R times T divided by P. So just remember the molecular weight kitty cat. The kitty cat sweeps his dirt over his pee, when he goes to the bathroom. So that's the easiest way to remember. This is dirt, and this is your pee. I can calculate the molar mass of a gas if I have 0.06 grams and it occupies 750 milliliters at 385 millimeters of mercury at 35 degrees Celsius. So there's a couple of things I have to convert right away. I have to convert 750 milliliters to liters. So because I always want my correct units to be liters when I use the ideal gas equation. My pressure, I want it to be in atmospheres so I can use the right value of R. I can use this value of R. You don't have to do it if you use a different value of R, but it's easier for me. So I take 385 divided by 760 and get my pressure in atmospheres. And then I convert temperature to Kelvin by adding 273. Now I need to know the density. The density, remember, is mass divided by volume. So if I take my given mass and divide it by my given volume, I find out that it's 0.811 grams per liters. Now, remembering the molecular weight kitty cat that sweeps his dirt over his pee, you can see that I'm finding the molecular weight, and I know the density, I know R, and I know T, and I divide it by my pressure in atmospheres, and then I get 40.4 grams per mole. This can help me identify the identity of the gas, and you can look at the molecular weights on the periodic table to help you understand. So I really do most of my thinking inside the box.